Hi guys, I'm Radoslav and today I'm going to be explaining one of the problems from the CodeChef Long challenge. And the problem was called cell shell, and yeah, it was, I would say, medium, maybe medium hard, because it's constructive and like in general it's kind of hard to actually determine the complexity of one, not the complexity, but like how hard one constructive problem is. There was some math involved, but the main part was basically like ad hoc, or it's constructive, where you basically just need to consider some corner cases and to solve all of them. So yeah, without further ado, let's go to the problem statement. So in this problem, basically you were given some cells initially, which are n, and after that you wanted to basically add some additional cells to your set of initial cells, such that for every two cells there was a path of length, the difference between x's plus the difference between y's, between those two cells. Or in some sense you wanted to create a large set. You were given some cells and you wanted to extend the initial set so that there was a path between every two cells, that the distance of which was equal to the Manhattan distance between those two cells. Or in other words, like the whole set was connected and there was like a Manhattan path between every two cells. And yeah, you wanted to basically find the minimal size of a set, so that like there is at least one way to do this. And also you wanted to find the number of ways to create such a minimal set, modulo some prime, which was 10 to the 9 plus 7. And basically there were 3 subtasks. The first subtask was like very small, where you could just do some brute force. And after that, there was also you were also given some integer t, which was, in general, you use it mainly for the subtask. And yeah, for half of the subtask, like for the first subtask, like excluding the subtask with small constraints, you're only asked to find the minimal size and not the number of ways to actually create such a set. And yeah, that's pretty much it. The constraints are 10 to the 5, like, yeah. And yeah, this is pretty much the problem. And now I'm gonna go to the solution. As I already said, in this problem you basically have a lot of, not a lot of observations, but like there are some cases we need to consider, but I mean, it's not very hard if you actually you just start writing out some different observations, and then you're gonna realize that the actual solution is relatively simple. So yeah, the first thing you should actually start with is to consider how the answer will look. By this I mean, in the end you're gonna have some set of cells which you are gonna definitely take, and there's like a very specific form. And you can notice it's always something like that. However, they may be like something on top of here, which like basically decreases. I mean, in a way, it's not in this case, but like in general, the whole set always would look, it will look something like that, or it can also be in the other direction. And yeah, the main thing is that we're actually going to consider some cut, which is in this example, this red line. And we are going to consider every possible cut. And the interesting thing is, because the answer will always look like that, we are only interested, like if we try all possible cuts, like horizontal cuts, then we are only interested in the cells above, like from the cells above this cut, we're only interested in the leftmost one and the rightmost one. Because basically they define the spread of this thing, like above this cut. Because in a way, when you think about some Manhattan distance, and you already have a cut, you don't really care about the height, but you only care about how much to the left and how much to the right basically the initial cells are. So yeah, let's, for every possible cut, let's keep from the cells above, the leftmost one and the rightmost one. And we actually only care about their x values and not really the height. So yeah, after we try every cut, those are like, basically we have like two interesting values, which are basically the spread above a certain cut. And the other two things we are interested in is basically for the level just below the cut. In this example, it's basically this one. What were actually the borders? Or in other words, again, the spread. So in some sense, for the spread above, our x, like for the current cut, like the right bound will be basically here, this corner, while the left bound, or like the left interesting part from the part above, would be basically this side. So yeah, in a way, if we try all possible cuts, we can actually see what are the constraints that are definitely needed for our answer. We already know that the form will be like that. It's quite easy to notice. And now we just need to actually consider the different cases. So yeah, as I said, we're going to consider all possible cuts, starting from the bottom, for example, but also we can do all possible cuts from the top. And also, we are actually going to jump over the rows where there are no fixed squares. Because in some sense, if we have a fully empty row, we can just ignore it, because we are definitely going to consider this cut on the row above. So yeah, in some sense, we don't really need to consider all 10 to the 5 cuts, although that still can be done and it's still fine. But in my opinion, it's easier to implement the whole thing if you just jump through the consecutive parts where there are, I mean, basically jump over the rows where there are no fixed squares, because in a way, the cuts there don't really matter. And yeah, as I said, let's go through the cases now. And in general, there are two main cases where some of them are symmetric. So overall, there are like actually 4 cases. No, actually even 5. But like, if you consider the symmetries, there will be only 2 cases. Maybe 3, depends on what you consider a case. But yeah, without further ado, let's actually go to the cases. So yeah, imagine that we have the following construction. The top 2 squares in general will be basically the thing above the cut, while basically like the 2 interesting borders above, while those 2 squares will be the interesting borders below. And in this case, we can notice that the thing we need is actually, we want the whole segment in basically here to be full. If the 2 borders were as like in this example. Why is this true? Because if this is like the minimal set we actually need. Because if we had something, well, if we didn't have this thing full, like if some of the cells between here were basically not there, then we definitely couldn't go for example, if we didn't have this cell, then if we tried finding the minimal distance from this cell here to like, yeah, sorry about that, from this cell here to something here, well, actually something in the same row, then the answer would have been 1 more than actually it needed to. And I mean, if we had like the Manhattan distance, this means that in a way, like we definitely need those cells to be there. And if we actually have those cells, then this is like actually the minimal set we need so that the constraint is satisfied. So in some sense, it would be like the intersection of the above range or spread and the below spread. Because like, I mean, the intersection of this interval and this interval, if we project them on the x-axis, it would be just like this range. And I mean, we want like all of the rows in this cut, like as I said in the previous, I mean, as I already said, we are going to jump over the empty rows, and like here we have a bunch of empty rows. And in this case, like we want this whole thing to be full. So yeah, that's like basically the first constraint. And yeah, it's relatively easy. We basically like when we go from the bottom and we consider every possible cut, we basically maintain basically like the current spread of the current row, and we look at the I mean, for the suffix or like all of the initial cells which have a y greater than the current y we are looking at, we basically get the minimal x and the maximal x. And yeah, we basically intersect those ranges. It's easy. It's basically like taking the smaller right bound and the large right bound. And we actually want the whole this whole set to be full. So this is basically like the first case, and obviously in this case you just want to add to the answer the height multiplied by the length of the intersection. I mean, basically like in those empty rows you're gonna just need exactly those cells. And you can notice that because we are taking every possible cut, those are needed, and they're actually also sufficient to guarantee that our set will have, I mean, that our set will be okay. I mean, those, if we just have like those sets for every possible cut, then our set will actually be sufficient. And yeah, I mean, after that we have the second variation of this case, when one of the ranges is actually inside of the other one. Similarly, we actually before that, for the previous case, obviously this construction could have been also the other way around. I mean, basically, if this range was to the right, I mean, in some sense here, like basically like the mirroring of this case. And then we would again have basically just chosen the intersection. Similarly, in this case, we actually have a mirroring, but like this time a vertical mirroring, like the mirroring by here. But when one of the ranges is inside of the other one, we can again notice that the minimal set we need so that the final set would be sustainable is to just fill the whole rectangle here full of black cells. And then, I mean, whichever, I mean, in this case, whichever segment you take, the final set will be fine. Also, I mean, after you go from, if you have this case, you also need to somehow maintain, because, I mean, as I said, we are moving this cut, and in a way we need to also maintain the current spread of like the row just below the spread. Obviously, when we have such a case, we are just going to keep this one and this one as the new endpoints for the row above. Well, in this case, yeah, sorry. Well, in this case, we are going to keep basically this thing as the border for the row above. Don't forget that this is the maximal right bound of some row above, and this is like the maximal left bound of some row above. So yeah, we are basically going to just keep this one and this one for the row above. Similarly, we have like a lot of different cases, and we just, I mean, basically we just go for all possible cases, and that's how we maintain the rows. So yeah, as I said, this is basically how we maintain our spreads, like while we are moving our border above. And yeah, this was basically the first case. There are like two variations. The first one is the two rows just intersect, while the second one is basically one of the ranges is fully inside of the other one. And okay, basically after the first case, we are done with the cases where the two ranges intersect. And now we have the second case where the two ranges actually don't intersect, and they're like that. So basically like there's, you can, I mean, yeah, they basically don't intersect. And in this case, you can, I mean, before that, obviously you can also have the mirroring of this one if the upper range was actually to the right of the lower one. And again, you could have achieved something without an intersection. And in this case, you can basically notice that the minimal construction would be just a path between, yeah, like a path like that between the left thing of the bottom row and the right thing on the top row. And obviously, I mean, you can notice that you just can get any path in this rectangle, but all paths have actually the same number of cells. So to actually get the answer, you can simply get, I mean, this path always has length equal to the Manhattan distance between this cell and this cell. So you can just, if you want to just find the minimal number of cells, you just add the number of cells in this path. And yeah, basically like those are all of the cases, and they're actually sufficient to find any set. You basically just move this cut and you consider the different cases. And I mean, to actually get to this solution, you basically just need to start by thinking how the answer will look. And after that, it's relatively straightforward. And obviously you can compute this in linear time, depending on n. You can also do like n log. The constraints are relatively low, so this will also pass. But yeah, finding actually the number of additional squares is very easy. You just go through all of these cases. In the first two, you basically find the intersections of the two ranges, and you multiply, and you basically add to the answer the difference between the heights multiplied by the length of the intersection. While in the second case, you basically just add the length of the path to the answer. And yeah, if you just go through every possible cut, you're done, and that's your answer for the number of additional squares. And now, like, how to actually count the number of ways. So, I mean, first of all, obviously, in the first case, there's exactly one way to fix those additional cells. I mean, you basically definitely need this set, so there's exactly one way to fix this set, and you don't really gain any. I mean, there's like basically just one way to fix this set when you have a cut of this form, and everything actually comes from the case where we have a path. And what you can notice is that in this case, we basically want to find the number of different paths between this cell and this cell, or like equivalently if we had the mirroring of this case. And this is actually equivalent to the well-known problem of you're given two cells and you want to find the number of paths from the top one to the bottom one if you go just right and down. Because if you go right and down and you don't really exit this small matrix, then obviously this will be any Manhattan distance. And yeah, to do this, it's like basically like this is a well-known problem, and there is actually a constant solution to it if you have like the pre-compute, and you know that actually this is equivalent to a binomial coefficient, which is for like the height plus the width over the width or over the height. And why is this true? Well, mainly because in a way you basically have definitely h plus w moves, and you want to choose exactly w of them to be down, and all other moves will be to the right. Similarly, like you can also choose h here, like it's the same answer, and this way you basically, like, if you just fix the positions of the down moves, you're gonna get like all possible ways to get from the top to bottom, and so this can be easily computed in constant time. And yeah, basically the answer is just the product of those combinations for like all possible, I mean, if you consider all possible cuts and you multiply over the, I mean, in the first case there is exactly one way to actually fix the cells, while in the second one we want to fix some path, so there are like this combination number of ways to fix this path. And yeah, what you do is basically just multiply all of those coefficients, and that's your second answer. And like if you pre-compute the factorials and the factorial inverses, know that for the factorial inverses we can pre-compute them in linear time, or if you just pre-compute the largest one and then go back from it to, basically, I mean, it's like, you can also do like n log here, but you can also do the pre-compute in linear time, and then every combination can be also found in linear time, in constant time, like every particular combination. And yeah, this is like pretty much the solution. This problem is kind of easy if you actually think how the initial set will look like. I mean, not the initial, but how the answer set would look like. And if you know that, then it's basically considering a lot of cases. Not a lot. You know, it's actually even just two. And yeah, that's pretty much it. Thanks for watching, and see you next time.